So today we're gonna learn about phase diagrams. And phase diagrams are very important because when we combine two elements, we need to look at phase diagrams to see what is the resulting phase or what is the equilibrium state. So phase diagrams are generated based on thermodynamical equilibrium, meaning within a long period of time, two elements are mixed and observe what type of phases they are making at a certain composition of mixture and at what temperature. So phase diagrams therefore is going to tell us what is the phase of a system at a certain composition and at a certain temperature. So how many phases form? So it doesn't have to be just one phase, it can be more than one. And what is the composition of each phase? How much of, let's say in the image we are seeing copper and nickel is mixed, and we are seeing they are forming two phases. So these are thermodynamically equilibrium phases. So phase A and phase B. Both of them have different structures, different properties. And what is the composition of each phase, meaning what is the amount of nickel or copper in phase B, or what is the amount of copper and nickel in phase A, or how much of the overall alloy the phase A is or phase B is, what is the percentage of the phase B, so amount of each phase. So we're going to understand phase diagrams and we're going to read information from the diagrams. Let's learn about solubility limit. So when we say, let's look at some terms. Solution means one single phase. It can be a solid phase, solid solution, or liquid phase, a gas. These are all single phases. And a mixture is more than one phase. So in terms of solubility limit, think about water and sugar system. You keep adding sugar to the water. First it dissolves and you just have one phase, which is liquid. But then as you keep increasing the sugar amount, it becomes concentrated. The solubility limit is reached. The water cannot dissolve the sugar anymore. So the solution becomes saturated with the sugar. So it is not capable of dissolving the sugar anymore. And therefore it's going to separate into two separate phases, sugar and water. So definition of the solubility limit is therefore maximum concentration for which only a single phase solution exists. When you think about sugar and water system, of course the solubility of sugar will change depending on the concentration, depending on what type of temperature, what is the temperature. They all change the solubility of sugar in water. So we are given a phase diagram of sugar and water mixture. So here, as we see in the x-axis, we are seeing the composition, weight percentage of sugar. And it is increasing from left to right. Okay, so here 100% sugar, here 0% sugar means water. So on the y-axis we are seeing temperature. Now the phases are separated. So you see L represents liquid solution and S represents the solid sugar. and different regions, different phases will be thermodynamically in equilibrium. So depending on what composition and what temperature you choose, you will have a different phase which is thermodynamically stable. What I'm trying to say, for example, if you have, let's say, 80% sugar and the temperature is 40, and then this is the phase region that your point ends. So that means you have liquid and solid sugar in equilibrium. Okay, so this wasn't just an example here for you guys to understand. So let's look at now the example. It says, what is the solubility limit for sugar in water at 20 degrees C? So as you can see, at 20 degrees C, so this solubility limit line is showing us where we cross from liquid to liquid solid sugar formation, right? If I go further here, that means at 20 degrees C, if I go further compositions, then I will have solid sugar solid sugar in my system. But where does it start to form? It starts to form at the intersection of that solubility limit line with the temperature line at this point, right? Okay, so now then what we need to do to start from 20 degrees C line, let me choose different color here. We go to the intersection of the temperature line with the solubility limit line and go down to read 65%. So that means at 20 degrees C, if you have composition of sugar lower than 65, you will have liquid, which is the syrup itself. So sugar dissolve and form the syrup. And then if you go above temperature, above compositions of 65, you will both have the sugar and the liquid. So this is the information we obtained from the phase diagram. We need to understand the difference between the terms. Here, when I say components, that means we are talking about the elements or compounds which are present in the alloy. Like we are mixing aluminum with copper, we have two components. But the phase is, they are maybe forming a solid solution together, right? So the phase is physically and chemically distinct material regions that form. And in this microscopic image, we are given the structure of an aluminum copper alloy, and we are seeing that we are seeing two different phases because they are basically physically different. And one of them is called alpha, the darker phase, and beta, which is the lighter phase. Both are solid solutions of aluminum and copper. Overall, the system has two components and two phases. So both the temperature and the composition is affecting what type of phase will be in equilibrium. So if you again look at the water-sugar system, and as a function of composition and temperature, we are seeing what are the phases that are in equilibrium. So here, if you keep the composition the same, think about you are going from point A to point B. How can you do that? So you keep the composition the same. It's a vertical line. But let's say we are increasing the temperature of the system. Therefore, I travel from point A to point B. Now at point A, I had solid sugar in the system together with the liquid. Okay, so it was saturated and there was solid sugar in the liquid. Now if I increase the temperature, I go from A to B. Now I have the sugar dissolved again, because at that point, the point B, I have liquid as the stable phase. So that means at point A you had two phases, sugar and the liquid. And when you increase the temperature, you end up with having just one phase, which is just the liquid, because the sugar now dissolved. You reached the solubility limit and go above the solubility limit. So let's say you are at a constant temperature and you are changing the composition. Let's say you are adding more sugar. If that is the case, let's start from point B, where we just have one phase. And we are going to point D. We just keeping the temperature constant, but we are increasing the composition. So if you increase the composition, you are again going from one phase to two phases. There is again sugar. You can observe as another phase inside your liquid, because you have now thermodynamically different phase. Liquid and solid is mixed inside your system. So as you can see, what does this tell us? Depending on the temperature and depending on the composition, different phases will be thermodynamical equilibrium. So different phases will exist in your system, okay, depending on what your composition is and what your temperature is. And we learned about solid solubility, right? For a copper and nickel system, they both have FCC structure. Their electronegativities are similar, atomic radius similar. So because they have so close numbers in terms of their electronegativity and atomic radius, basically this suggests high solubility in between each other. In fact, nickel and copper are totally soluble in one another for all proportions. So it doesn't matter what composition you have, they can dissolve in each other at any composition. This is a binary system, and it is represented by binary phase diagrams. So we now gonna take a look at the phase diagram of copper and nickel. So of course the phase diagram will show us what type of phase you have as a function of temperature and composition. Usually when the phase diagrams are plotted, the pressure is always the same, which is kept at 1 atmospheric pressure. So in this case, we said it's a binary system, means we have just two components, copper and nickel. You can change the temperature and composition because they are not depending on each other. So in this phase diagram, for example, we are seeing two phases. Okay, so we have two components, copper and nickel, and we have two phase, which is liquid and solid, and the solid is FCC, solid solution. But we have three different phase fields, because we are seeing liquid, we are seeing liquid and solid in equilibrium, and we are also seeing the solid solution alpha as representing three different phase fields. Okay, so these are. So the copper and nickel system is termed isomorphous binary phase diagram. This term is because they have complete liquid and solid solubility of the two components in liquid and the solid form. So binary means two components. Okay. We need to understand that for metallic alloys, the solid solutions, like mixture of copper and nickel, when they dissolve in each other, these solid solutions are represented by Greek letters like alpha, beta, gamma, and the lines we observe in the phase diagram is separating the phase fields. Okay, so the line that is separating the solid solution alpha from the liquid and alpha phase region is called solidus line. And the line that separates the liquid and alpha mixture from the liquid phase is called Liquidus line. So here on the x-axis we have 0% nickel, because the x-axis is drawn as a function of the nickel, percentage of the nickel that is added. So at 0% of nickel you actually have 100% copper. And at 100% nickel you actually have 0% copper. So these points here, that point is actually representing the melting point of the nickel itself. And this point here representing, if I go above this part, right, representing the melting point of copper, pure copper. One is pure nickel, one is pure copper. But as you can see, the melting point is increasing as a function of nickel addition, because to see the melting point of the alloy you need to look at from the composition of that alloy. Go upwards, draw a vertical line as I did, and go to the intersection of the Liquidus line and then read the corresponding temperature on the y-axis. Okay. So as I said before, if you are given the temperature and the initial composition C0, okay, of that alloy, you know what the temperature is, what is the initial composition is, you can figure out what phases you have. For example, point A, we are given it is at 1100 degrees C and at 60% weight percent of nickel. It puts us to a point where we are at alpha region. So alpha is a solid solution, right? If we have a temperature of 1250 and the composition is 35 weight percent nickel, then we are at a position where it actually we are at the phase of liquid plus solid mixture. So liquid and alpha as a mixture exists in equilibrium. Now let's take a look at how we can determine the phase compositions. So if we know the temperature and the initial composition C0, then we can determine the composition of each phase. For example, consider an alloy which has 25% nickel. So automatically 65% is copper. Of course, you guys can understand that, right? So when I have an alloy which has 35 weight percent nickel, At temperature 1320 degrees C, what is the phase that is present? So let's look at it. 35 I locate from the x-axis, and I find the temperature, my temperature line TA, which is 1320, and I go here and intersection. I find that I am located in the liquid phase, so I only have liquid. So if that is the case, if you have one phase and then that means your initial composition and the composition of the liquid is the same. That means within the liquid also it is 35% nickel and 65% copper. Okay. If you are at point D, for example, which is at a lower temperature but the same composition, again you are at a point which is within the alpha phase region. Therefore, you just have a solid solution of copper and nickel. And in this case, again, you just have one phase. That means the composition of the solid is equal to the initial composition of the alloy. So again, the 35% of the alpha is nickel. So within the alpha phase, 35% of it is nickel and 65% copper. Okay. What about if we go to point B? We have the same initial composition, initial C0. So when that is the case, you start with the same composition, and we are given the temperature is 1250, and then it puts us to a point where the two phase is in equilibrium, which is liquid and alpha. So the question is, how much of nickel there is in alpha, or how much nickel there is in liquid? So to understand that, we need to draw a tie line. Tie line is the line at that temperature which connects the intersections of that temperature line with the liquidus and solidus line. So from the intersection of that tie line with the solidus line, if I go down and read the composition, that composition, because it's the intersection with the solidus line, is gonna give me the composition of the solid, which is the composition the percent of nickel inside the solid phase. So that means 43% nickel is in the solid phase. Okay, so the composition of the solid is equal to C with the subscript alpha, which is 43. Okay. So what about the composition of the liquid? To understand the composition of the liquid, this time I go to the intersection of that tie line with the liquidus line, which will give me the composition of the liquid. If I go down, Cl, which is 33%, that means within that liquid there 32% of is nickel. So this way we figured out the compositions of the liquid and composition of the solid. We didn't figure out what is the amount of solid or what is the amount of liquid. So this is an important difference. We just figure out the compositions of the liquid and alpha phase. So how much nickel in the solid, how much nickel in the liquid. It is not the liquid percentage or the solid percentage. That is different. We're going to take a look at that now. So if you know the temperature and the initial composition, you can determine the weight fraction of each phase. What does it mean? If you are in a phase that where you have liquid and solid in equilibrium, and the liquid and alpha in this case, that means you can figure out the percentages of alpha and percentages of liquid, how much liquid there is, how much alpha there is in the overall alloy mixture. So let's do the same example here, okay? And in order to calculate the weight fractions of each phases, there are equations used, and we call this lever rule. So these equations are given to us. For example, if you want to calculate the weight weight fraction of the liquid phase, you have to use this equation. Okay, and if you want to calculate the weight fraction of the solid alpha phase, you're going to use this equation. And let's see now how we're going to use this equation. Okay, so initially we have 35 weight percent nickel, okay, our C0, original composition. And at point A, with it corresponding to that temperature, we figured out that we just have liquid. So what is the weight fraction of liquid then? 100%, right? The weight fraction is 1. So we don't have any alpha. So alpha is 0. What about at point D? So the same composition, different temperature, corresponds to point D. At point D, we just have a solid, and the solid is the only phase that presents, meaning it is 100% solid, and the weight fraction is therefore it is 1. Okay, so because we don't have any liquid phase. So if we are at the point B, and at that temperature, we are here in point B, where we have two phases, liquid and alpha. What you need to do to calculate the weight fractions of each phase? So let's say you want to calculate the weight fraction of the liquid. Of course, you're gonna go ahead and read the intersections of Liquidus and solidus line. First, you're gonna find the composition of the liquid and composition of the alpha, as we did in the previous slide, right? So this was the composition of liquid, and this was the composition of solid. So using that information, the composition of liquid and composition of solid, we can calculate the weight fractions. So in this equation, it is given to us as S over R plus S. So those are representing these lengths or the ranges of these as letters are given in us in the phase diagram. So this is R, this is S. So I don't like this type of equation actually written this way. What I can tell you is we can use this equation because it is the same, right? So S means the composition of alpha minus the initial composition, because that is the distance, right? Distance S is 43 minus 35, which is the composition of alpha minus the original composition over the sum of the R and S, meaning 43 minus 32, meaning C alpha minus CL. Okay, so the equations will be given to you this way. Okay, and from here now you can calculate the weight fraction of the liquid. So all you have to do, C alpha is 43 minus C0 is 35 over C alpha is 43 minus CL is 32. This will give you 0.73 or 73% of the the overall alloy is liquid at point B, okay? And the remaining, of course, is gonna be the solid. But to find the solid, you can again use this equation. That is gonna be C naught minus CL over C alpha minus CL. Okay, you can use it to figure it out yourself. Okay, so in this slide, we are going to be shown how to derive this lever rule. Okay, so we talked about tie line, which was the line that connects the phases in equilibrium with each other. And this is also called isotherm because it is at a constant temperature. So what is the lever rule? This is a rule that is used to calculate the fraction of each phase, and we have just used this equation. But how it's derived, think about, we are at point B right there, right? And the phases of liquid and solid alpha, they are in equilibrium, their weight, right, their masses. So what are their distance to the point B? Is R and S. So basically, because this has to be in equilibrium, that means M alpha times S should be equal to ML times R. So based on that, you can solve this for M alpha and say ML R over S. Okay, now, if you want to calculate the weight percentage of the liquid, that means we are just dividing weight fraction of the liquid. That means we are just dividing the mass of the liquid to the overall mass, right? Mass of the liquid over the overall mass, meaning mass of the liquid plus mass of the solid. So this is gonna give us the weight fraction of the liquid phase. So if you come here, put this in here, okay, put it in M alpha, and what you're gonna see is it's gonna give you S R over R plus S over R plus S. So we know S is C alpha minus C naught, and we know R plus S is C alpha minus CL. So this is R, remember, this is S. That's where the difference is coming from. So we have just did, but this is to show you how it was actually derived. Alright, so if we want to analyze the cooling of the alloy, which is at 35% nickel, can we look at how the microstructure changes, like under microscope, right? How the microstructure changes as a function of temperature. Let's say at this composition we have an alloy. We start with point A and then we go down, cooling it down until we come to point A. Okay, so raised. So let's see how the microstructure is changing. So at point A we have a pure liquid and its composition is 35% weight nickel. And when we reach point B is located in liquid and solid phase region. That means within the liquid now, the alpha phase is starting to nucleate. And you can see at point B, the microstructure shows that in the background we have liquid, which is shown with green, and solid phase, which is the blue phase, is starting to solidify. We have two phases. So what about the composition of each phase? Remember, we are looking at the tie line and intersection of that tie line with the liquidus and solidus line. And its intersection with the liquidus line shows us 35. Its intersection with the solidus line shows us 46% nickel. That means that The liquid composition is 35 weight% nickel and the solid composition is 46% nickel. As we keep cooling down, we come to point C. Now the point C again, if you look at under microscope, now the grains, the nucleated particles of the alpha now getting bigger, right? Inside the liquid, they are getting bigger, growing, because we are cooling it down, we are solidifying the material. So at point C, if we want to learn what is the percentage of the nickel in liquid and alpha phases, then we again look at the intersection of that tie line with the Liquidus and solidus line. And Liquidus line intersection shows us a composition of 32. That means we have 32% nickel in the liquid, and again 43% of nickel in the solid, because it's the intersection of that tie line with the Liquidus line. Right here I read it. And then we keep cooling it down. Now we came to point D. We still have a mixture, but the solid is getting bigger, as you see with the blue here. And what about the percentages of the compositions of the liquid and alpha? Again, the same way we read 24 and 36. 24 for the liquid composition and 36 for the solid composition. After that point D, we kept cooling down and we came to point E. At point E, we just have a solid phase, and you can see how the solid form with grain boundaries, and the composition is 35 weight% nickel. Now, there are differences between doing a slow cooling and fast cooling, and the phase diagrams are obtained for slow cooling rates when we provide enough time to atoms to diffuse into their equilibrium structure. So if you do slow cooling rate, that means at the end means if when we reach the stage A, we have a uniform structure, means everywhere the nickel composition is 35%. But if you don't do it so fast and don't allow the atoms to reach their equilibrium, you do it fast, that means you will have a chord structure. That being said, the initially solidifying phase will have 46% nickel. Here we see it, right? Initial nucleates, they have 46% nickel, and you need to end up with 35%. If you do it slowly, you end up with 35%, but if you do it fast, what's going to happen? You will have different layers of the same alloy, but the composition is different throughout the structure. So the last part that solidifies should have 35%, but there's going to be a range of compositions in the structure. It's not going to be a homogeneous structure because you don't let enough time for atoms to move to their equilibrium positions. Here, as we have seen in the strengthening of materials, so if we look at the copper-nickel system, you can see the effect of solid solution hardening on the tensile strength and ductility. And as we increase the composition of nickel in the alloy, the strength is increasing initially and then reaches a certain point, 60%, let's say, reaches a maximum. As you keep increasing the nickel amount, it's actually causing a decrease in the tensile strength. So that means actually there is an optimum composition where you actually achieve the highest tensile strength. This is the same, of course, tensile strength. If you look at the ductility, similar behavior. Of course, this time the ductility is decreasing with increasing nickel concentration until a point, 60%, and then again increases. So this 60% of nickel seems like the optimum composition for the copper nickel alloy. So these tests has to be done for different types of alloying systems to figure out what is the optimum composition at a certain temperature. So they kept the temperature constant here, and then they are looking for how the properties changing with the addition of nickel. Now we're gonna take a look at binary eutectic systems. Binary means again two components. Eutectic means this mixture has a special composition with a minimum melting temperature. So in this case we are seeing a copper and silver system. And if we look at the phase diagram, again as a function of temperature and composition of silver, different types of phases are available. We see alpha, liquid, beta, and in some regions, for example here, only alpha is stable. In these regions, for example, liquid and alpha together stable. In here, liquid stable, beta, liquid beta, and alpha and beta. So again, depending on the temperature and composition, you can read the phase diagram and see which phase is present in that circumstances. So now alpha has a limited silver solubility. We are seeing that if we look at the maximum solubility of silver in alpha is around 8. So 8% silver maximum soluble in this structure. So what about beta? Beta means, if you are looking here, maximum solubility of silver is actually very high. So it can solve up to 95 or so. So that means like 5% copper is soluble inside beta. Okay, so these are the solubility limits, maximum element that we can dissolve in that system. And we are seeing something. So in 0% silver, that means we have 100% copper. And its melting point is right there. I mean for pure copper, and for pure silver the melting point is there. So when you have a eutectic system, these when they are put together, silver and copper, they will have a low minimum melting point at a special composition. And that special composition you can see, because the melting point is when you go from liquid to solid phases. So in that position, in that composition, which is the eutectic composition, with the symbol E it was shown, subscript E, this composition 71.9 is the eutectic composition, and it is the material is reaching a minimum melting point, which is, you read it from here, approximately 779 degrees C. So TE is therefore the liquid, the eutectic temperature. CE is the eutectic composition. Okay, so eutectic reaction is then, we are going from liquid, which is at a composition of CE, and we are going to two solid phases, alpha and beta, when we cool it down. So alpha and beta compositions is going to be read like this. Let me show you. Erase, and we choose some color. Okay, so this composition, you go to draw your tie line and then go here and read 8% as the alpha composition and 91.2% for the silver composition. Okay, so this intersection is 91.2. Okay, that's it. But the liquid composition was this one, which is 71.9. Okay, so the question is coming. Example. This is lead and tin eutectic system. We have a alloy composition of 40% tin. Of course, that means 60% lead automatically, right? And which is at a composition of 150 degrees C. So now if you want to determine in your phase diagram, tin and lead phase diagram, you need to be careful what is given to you on the x-axis. Because in this case, x-axis is showing us weight percent of tin. So therefore, okay, so we are given, we need to look at the x-axis, and then here you have tin, right? And 40% tin, then you need to look at the concentration of the tin to be able to read the x-axis, okay? So this is your original composition. And the temperature given to us is 150. So we look at the intersection and we find that we are located in a region where alpha and beta solid phases are in equilibrium. Alright, so that means I have both alpha and both beta in the system. And what are their compositions? What are their compositions? It's easy. You look at the tie line, same temperature line. You start from here to here and look at its interaction between the phases. So if you look at the intersection of this tie line with this line, it should give you the composition of alpha. And if you look at the intersection of this tie line with the beta phase, it should give you the beta phase composition. So in alpha phase you have 11% tin, in of course the remaining is the lead. In beta you have 99% tin, which is 1% lead. So now we know that. What about how much alpha and how much beta I have in overall alloy? This is the weight fractions of alpha and beta, right? So in order to do that, we're going to use our equations. So our equations was like that. So all we have to do is plug in the information, right? So this is 99 minus 40. This is 99 minus 11. And you get 0.67%. 67% or 0.67 weight fraction. So what about the weight fraction of beta? The remaining should be, but you can calculate it again from this equation. So this is a typical phase diagram question that can come in the exam. A lot of questions can be asked. So you guys need to learn how to read the phase diagram. And if you're having difficulty after the lecture, please come and ask questions to me. Come means text me, of course. Unfortunately, that's the reality here. So you guys gonna text me or come to office hours and ask questions to TAs and try to learn about it, okay? Okay, so another example here. We have still 40% tin alloy. So our, again, original composition is 40%. This time the temperature is changed. The temperature is 220. So that means I have liquid and alpha in equilibrium. So what is the composition of liquid and what is the composition of alpha? Again, we look at the intersection of the tie line and read alpha composition here and read liquid composition here. And it is 70% tin in alpha, 46% tin in liquid. From that, again, you can calculate the weight fractions of the solid and liquid phase also. So how much alpha we have? 0.21. How much liquid we have? 0.79. So 21% alpha, the rest is basically 79% beta. And within this alpha, the composition of it 17% tin. Okay, in this system again, tin and lead system, we are seeing as part of the phase diagram up to 30% of tin. If let's say you have an alloy which is the composition is less than 2% tin, it is shown with the purple line C0. And if we want to analyze in eutectic systems how the microstructure is changing, at this point right there we are only have liquid, and as we cool it down we come to liquid and solid phase here. So both of them are in the equilibrium. So the alpha solid is forming from the liquid, green, and then as we keep lowering it down, at this point we should only have alpha in the system. So you can see how the grain boundaries are forming in this pure solid phase. So we can see all of them have a composition of C0. Let's say you have an alloy and the concentration of the alloy, the initial composition of the alloy is in between 2% and 18.3%. So somewhere here. If this is our original composition, so let's analyze the microstructural developments. Okay, so we start at this point and start cooling down. Again, at that point we just have liquid. That's what we are seeing in the microscope, and then we cool it down, come to this point. Now we should have liquid and solid, liquid and alpha, and we are seeing the alpha is starting to form inside the liquid. And then as we keep cooling down and come to this point, we only have alpha. We can see that it's only solid alpha with polycrystalline structure, grain boundaries, alpha grains. Now as we keep lowering, we come to this point, which is from alpha. Now beta starts to form, so we have both alpha and beta. So because we are cooling down, we started with the alpha grain structure, and from the alpha grain structure beta grains are forming, which are shown with the red. Right now two solid phase is in equilibrium, so we have alpha grains and small beta particles in the structure. Now let's look at if we are at a eutectic composition. If we are at a eutectic composition, that means our original composition is equal to eutectic composition, and we do the same cooling and analyzing the microstructure. How does it look like? Again, we start with the liquid now, and from liquid, as we cool it down without any other phases, as we pass the eutectic temperature, when we go down, what happens from liquid, two solid phases are forming, right? So that means you have the mixture of alpha and mixture of beta, and eutectic structure looks like this, a lamellar structure. It is alternating layers of alpha and beta. That is how they are characterized. So under microscope, when you see such a structure under microscope, layers of alpha and beta, so whites can be alpha, blacks can be beta. So if you see that alternating layers of alpha and beta, that is a characteristic property of a eutectic microstructure. So this is just an illustration that how from the liquid the solid eutectic structure is forming. Okay, so of course the solid particles will start to form within the liquid, and remember the beta phase is rich in tin, whereas the alpha phase is rich in lead. So what happens as it grows, tin is flowing to the beta phase, and lead is flowing to the alpha phase, and it keeps growing. Okay, so Let's study this phase diagram, Eutectic system, and let's look at how we can apply the tie line principle and how we can calculate the weight fraction of each phase. So suppose now we have an alloy, and the composition of alloy is in between 18.3 and 61.9. So our composition is somewhere here, okay? And seems like it is 40%. So again, we start with the liquid phase. As we cool it down, let's say we come to this point just above the at eutectic temperature, and we can see that liquid and alpha is in equilibrium. Okay, from the liquid, alpha solid is forming. And how you gonna now calculate the composition of alpha and composition of liquid? Again, the tie line, you go to the intersections and you read that 18.3% thin is in the alpha, and you read this 61.9% is in the liquid, because you are looking at the interaction of with the liquid line, right? So we figured that out, it's given here. So what you can do, take the 40 as the composition, original composition, plug into your equations that we have learned to calculate the weight fractions. It is 50-50. So that means 50% liquid, 50% solid, and their compositions are given here. So if you go below the eutectic temperature, you should have alpha and beta. But now remember how the microstructure is going to look like. So we had this microstructure, right? Liquid and alpha. Now when you go from here to here, basically from the liquid you need to form alpha and beta, because that is the eutectic reaction, right? So you already have the alpha particles here, and the remaining liquid will turn to lamellar structure of eutectic structure, alpha and beta layers, alternating layers on the background. Okay. So in this case you do the same calculation, and it's very close, the numbers are very close here. So we have this point, we read this intersection again nearly 18.3, and let me get another pencil here. You read go to the beta intersection and read the beta composition and plug those in. You find the weight percentages of alpha and beta. So hypoeutectic and hypereutectic means before the eutectic and after the eutectic composition. So we have seen how it looks like in all of these compositions, like before eutectic, how it was, right? If we have a 50% thin, then it's gonna look like, because we are coming from liquid to alpha and beta phase. So the alpha will stay in the structure and the liquid will turn into alpha and beta, like we are seeing in the microscopic image. And this is how it look in eutectic composition. And after the eutectoid composition, it's called hypereutectic. And in this case we start from, right, we have beta and liquid, and then when we cool down, liquid turns into alpha and beta. This time beta particles stay and the liquid converted into the eutectic structure, alpha and beta composition. So for some systems there can be compounds forming rather than solid solutions, and these compounds, of course, the name compounds mean they have distinct chemical formula. So certain number of elements will react with certain number of other elements. So these are called intermetallic compounds. As you can see here, lead and magnesium phase diagram. we are seeing a compound which is 2 magnesium comes together with 1 lead element. So it is magnesium 2 lead. So this is the name of the intermetallic compound. So this is represented in a phase diagram as a vertical line, as you can see. The reason for that, as written here, because of the stoichiometry, because the composition of a compound is a fixed volume. What you can read about this intermetallic compound is its melting temperature, because here we are on this line, right, and the melting temperature is right there. So it's approximately 550 as indicated with point M here. Other things you might notice: the solubility of lead in magnesium is extensive. It's relatively indicated by the large span of the alpha phase. However, the solubility of magnesium in lead, which is shown with the beta, is very narrow. So it's very limited. Besides eutectic reactions, whereas we learn in the tin and lead phase diagram, where liquid goes into when it's cooled down alpha and beta phase, there are also other types of reactions like eutectoid, peritectic. So when we are talking about eutectoid, one solid phase will go to 2 solid phase. Okay, so here in the eutectic, from liquid we go to 2 solid. In eutectoid, from 1 solid gamma you go down to 2 solids. The difference is you start with a solid phase, here you start with a liquid phase. Okay, so, and peritectic is when you have solid phase and liquid phase will come together to form a second solid phase. So delta solid comes together with liquid, and when it's cooled down forms gamma solid phase. That is the peritectic. So here it's also giving you, so S means from solid to solid, from solid liquid combination to one solid. So these are the characteristics of all these reactions, and they are giving examples from different phase diagrams. We have seen this in tin lead phase diagram. These eutectoid and peritectic reactions exist in iron carbon phase diagram. Here we are seeing an example of eutectoid and peritectic reactions. Here we have the copper and zinc phase diagram. So at point A we are given it is a eutectoid transformation. Upon cooling down from delta we are going into gamma and epsilon, meaning from one solid 2 other solids are formed. What about the peritectic? When we start from this point and cool it down, it goes from gamma plus liquid to delta. So from liquid and solid combination you go to form one solid. So as you can see, very complex phase diagrams also exists. Like in this case we are seeing copper and zinc. So iron carbon phase diagram is the most important phase diagram you ever gonna see, because this phase diagram is used in the production of steel, cast iron, and that's why those are the most commonly used materials. Therefore, this phase diagram is very important. So it is, as you can see in the x-axis, the carbon range is given, but you see it's given up to 6.7%. Because at 6.7%, what we have is an intermetallic compound called cementite, iron 3 carbon. And this is the only important part of the phase diagram because it gives information about steel manufacturing, steel production. Because the steel, remember, is a combination of an alloy of iron with carbon. So that's why only this region of that phase diagram is actually very important. So in the iron-carbon phase diagram, we are seeing two important points. You see at point A, there is a eutectic reaction because when we cool down from liquid, we are going into two solid phase, which is gamma and cementite. So the gamma is called austenite, as you can see here. So these names are important. Gamma is the austenite, and there is also one eutectoid reaction at point B where we go from austenite solid to, upon cooling, we form alpha solid plus cementite. So from one solid we form two solids, so it's called eutectoid. So this structure of iron, the structure of alpha plus cementite is called pearlite. So together they have a name. Here you can see. Pearlite looks like this because we know this is similar to eutectic structure, right? Alternating layers of alpha and cementite. This is hypereutectic steel. So before the eutectoid composition. So as you can see in the iron-carbon phase diagram, the eutectoid temperature is 0.76% carbon here. This is where the reaction happens, right? We go from gamma to pearlite, which is the combination of alpha iron to cementite. So at this point and below that, so this is where we have the eutectoid steel, but now we are talking about hypoeutectic, meaning before the eutectoid composition. That means in between 0 to 0.76. So somewhere in between you can choose the composition, which is C0, as you can see. Let me delete that. Okay, so you can see C0. At that composition, let's start with an alloy at this temperature. Okay, at this temperature, we have only a gamma austenite. Okay, so it's an alloy of iron and carbon. And we are seeing a solid solution of iron and carbon, which is the gamma and called austenite. Upon cooling down, what we are coming here is right there. Okay, right there, what do we have? Here we have alpha plus, let me see here, gamma. So from austenite, upon cooling, you need to have the formations of alpha. And I think the alpha is shown here, yes, with the blue dots. So alpha is starting to form. As you can see, they are forming at the grain boundaries. Where are the energetic regions? Remember, atoms are more disordered in the grain boundaries, so nucleation of alpha from austenite starts at the grain boundaries. And we continue to cool down, right? We came here and we came here. This is above, a little bit above the eutectic temperature. Therefore, right now you have gamma austenite and alpha phase grown a little bit. So if we go below the eutectoid temperature right now, from that alpha, from that gamma, so the alpha will stay, okay? As you can see, it stays. But from that gamma, you need to form pearlite, which is the mixture of layers of alpha and cementite. This is how it actually looks like. If you can see a hypoeutectoid steel, as you can see, we have proeutectoid ferrite. Ferrite is the name of alpha ferrite. So here the alpha structure is shown with the white in under microscope, and we are seeing the lamellar structure of pearlite, right, these regions. Okay. So in this figure we are given how do we calculate the weight fractions if we have a hypoeutectoid steel, and then if we are above the eutectoid temperature. If we are above, as you can see in this point right there, right, this is our structure and this is the eutectoid temperature. If we are above that, what is in equilibrium is right there, is alpha plus gamma. So what are the weight fractions of alpha and gamma? Of course, you're going to read it the same way, right? There is the tie line here, and then you're going to read the numbers here. Okay. And from the equations we have learned, you can calculate it easily. What about if there is the weight fraction below? So we are talking about below. Let me see, choose a color here so it's visible. Let's choose this. Okay. No, not this. This. Okay. So let's say you are at this point. That means you have alpha and then pearlite structure. So how do you read the composition? This time, because you are below the eutectoid temperature, your tie line is gonna be this big because there's cementite, right? So from here you read alpha composition, and from there you read cementite composition. Of course, this will give you only the weight fraction of pearlite is actually equal to the weight fraction of gamma, because from gamma you form the pearlite, right? So but if you want to find the weight fractions of alpha and cementite inside that pearlite, you can use the formulas that we are provided. So now the idea is the same, you guys can understand. Now we are looking at hypereutectoid steel. So eutectoid composition was 0.76, and now we are talking about up until this range, right? So within this range means above eutectoid composition, you can choose a composition and analyze the microstructure. So we start with gamma austenite, and from that a cementite is forming, as you can see as you go down. cementite is forming. Now I have alpha and cementite in equilibrium. Then if you go below, if you are just above the eutectoid, then you have again gamma and cementite, as you can see in the structure. And if you go below the eutectoid temperature, now from that gamma austenite, it forms alpha and cementite structure, as you can see here. This cementite stays, this gamma forming the pearlite structure, which has alpha plus cementite. And how it is look like. See, these are cementites under microscope, and then you see the lamellar layer by layer structure we call pearlite. Okay. So again, the weight fractions are the same way. If we are above the eutectoid temperature right there, then you can read the amount of cementite and then the composition of the cementite from this intersection, and composition of the gamma from this intersection. So by using the same lever rule, you can calculate the weight fractions of the gamma and the cementite at that point. And remember, from cementite stays the same from gamma, pearlite forms. So the weight fraction of the pearlite is therefore equal to weight fraction of gamma, because the same, right? From gamma the pearlite is forming. And if we want to know the composition of alpha and cementite inside the pearlite, we need to use the lever rule again. Okay. Okay, let's look at an example. For a 99.6 weight% iron and 0.4% carbon steel at a temperature just below the eutectoid temperature, determine the following. So we are looking at the iron-carbon phase diagram and looking at the carbon composition of 0.4 weight%. So A, the compositions of cementite and ferrite, and B, the amount of cementite that forms in 100 gram of steel, and the amounts of pearlite and proeutectoid ferrite in 100 gram. Okay, so you need to understand we have a steel, and which is an alloy of iron and carbon, and it is 100 grams. So the weight fraction, the composition of this steel is 0.4%. So if we look at the iron-carbon phase diagram, first locate your composition, right? This is the composition. In the x-axis we are given carbon. Locate 0.4. Okay, it's somewhere here. And this is our original composition, and we are told that at a temperature just below the eutectoid temperature. So just below, this is the eutectoid temperature, right? Somewhere below that eutectoid temperature, we have to read the composition of, what does it ask? Let me see. The composition of cementite and ferrite. Okay, it's easy because at this just below the eutectoid temperature. Sorry, it's very late. My mind is not able to concentrate. Okay, so so we are talking about just below the eutectoid temperature, and we are seeing we want to find the composition of alpha and cementite, right? So like the tie line, we draw the tie line like this and go to the intersections like this and read the compositions there. Of course, if it's not very clear from the diagram, reading some approximate value is okay. But we read 6.7% for the cementite, and we read approximately 0.022 weight% of carbon for the alpha. Okay, so these are the ones that are inside the perlite. Now, using the lever rule with the tie line shown, calculate the weight fractions. Okay, this is easy because we know from the equation the weight fraction of cementite and weight fraction of, let me see what's asked. The amount of cementite that forms. Okay, so see, you have 100 grams of that material. How much of it is cementite? Now we are talking about the weight fraction. So if you find the weight fraction of the cementite using this phase diagram, as we have learned, which is 0.057, that means 5.7%. Okay? What is the 5.7% of 100 gram? And that should be 5.7 gram. So 5.7 gram of the 100 gram is actually cementite. So next, let's see what does it ask. We figured this out. The amounts of perlite and pro-eutectoid ferrite in 100 gram. Okay. So now you gotta remember. Here we had gamma and alpha, and from that, when we cool it down below eutectoid, this gamma went formed cementite and alpha ferrite, but also alpha remained in the structure. If you remember, we have alpha here like this, and then let's see, and lamellar structure, which is formed from gamma. So this formed from gamma to ferrite structure and cementite and ferrite, and this was the alpha. Okay, so we know what C naught is, which was 0.4, and we know C alpha, the composition of the alpha. Remember, this is just above the eutectoid temperature, so we are talking about this as a tie line here. So I read the compositions from there. I know C naught, I read C alpha, and C gamma is read from there, because there you have only alpha and gamma. And remember, the perlite composition was equal to the composition of the gamma, which is you can read from here, right? This one, 0.76. So we gotta find the weight fraction of perlite just above the eutectoid, and again the same way we calculated from the lever rule. That means we have 51.2 gram of that 100 gram is perlite. Of course, the remaining should be the alpha, right? So 100 minus 51.2 should be giving you the weight fraction of the alpha. So again, you can look at the virtual material science and engineering, and there are interactive phase diagrams you can check the microstructure how it looks like for different kind of phase diagrams. You can just Google VMSE, or I already sent you guys several links to that website. So sometimes this iron carbon system steel is added, other alloying elements are added to the structure, and there are reasons for that. If you want to control the eutectic temperature, eutectic composition, and induce some changes to that phase diagram, and people may want that because so controlling the working temperatures are important. So they add actually other alloying elements. So that is one of the reasons why people add alloying elements to the iron carbon alloy system. And you can see how eutectic temperature changes with the addition of alloying elements, and how different alloying elements changes the eutectic temperature differently. As you can see, adding nickel as a function of nickel element, the eutectic temperature is decreasing. Manganese is the same, but some elements like titanium, molybdenum, silicon, they are increasing the eutectic temperature. And we see the how elements addition of other alloying elements also affects the eutectic composition. They are also changing the eutectic composition on the carbon iron phase diagram. So their effect can be seen in here, right? So with titanium, all elements seems like they are decreasing the eutectic composition. So in summary, we learned about phase diagrams. These are important tools because we might want to know what phases present in the structure, depending on what is the composition, temperature, and we learned that we can actually get information like what is the weight fraction of each phase, or what is the composition of each phase depending on the temperature and composition. And we have learned that microstructure of an alloy depends on its composition, and whether or not cooling rate allows for maintenance of equilibrium. Meaning, remember, if we do slow cooling rates, usually we follow the patterns in the phase diagrams. But if we do very quick cooling of the structure, then the atoms may not reach their equilibrium state. So you might not observe the same structure that is predicted by the phase diagram. So important phase diagrams, phase transformation included eutectic, and peritectic. So this is it.